This is the second in a series of videos about enthalpy. In the last video, we just finished discussing how delta H and delta U are state functions, meaning the only thing that matters is the destination and not the journey. And so in this video, we're going to use that concept to illustrate Hess's law and talk about how to use it to do calculations. So if enthalpy delta H is a state function, it only matters about the initial and final state and not how you get there. So let's illustrate an example. So this is going to be enthalpy. This is going to be my initial enthalpy value, and this is going to be my final enthalpy value. So my delta H would be the difference between these two. It would be my delta H total. But let's say maybe this step, doing this entire reaction as one step, is difficult to do. And so maybe there's another way of doing the same reaction that takes two steps. So the first step would have delta H1, and the second step would have delta H2. And so what we know, because enthalpy is a state function, is that if we add the enthalpy of all the individual steps we used to get between the initial and the final enthalpy, those should add up to enthalpy total. And that is because enthalpy is a state function. Sometimes math is a really useful tool. And quick review, is this going to be an exothermic or an endothermic reaction? We are ending at a very negative delta H value, and we're beginning at a very high enthalpy value. So that is going to be a delta H total that is less than 0, a negative number, and so that is going to be exothermic. Good to make sure we still remember what those words mean. Okay, let's do an endothermic reaction over here to show that it's still true there. So let's say that this value is my initial value now, and this is my final. So my delta H is going to be this arrow. And so we're going from some number to a number more positive than that. So our delta H is going to be a positive number. So it's going to be endothermic. Okay, and let's take a more roundabout way of getting there. Let's say that instead of doing one endothermic step, let's say instead we first did an exothermic step, and then we did a very endothermic step after that. So 2 steps, but same initial and final enthalpy values. We can add up those 2 steps to get delta H total. And this is really useful because some reactions are experimentally easier than others. That's the whole reason behind this section, is that if there's an easier way to do a reaction, even if it takes multiple steps, we will choose that way of doing the reaction. And so the conclusion about this and the picture we just drew, that's called Hess's law. And Hess's law says just that. We can calculate delta H for a reaction from the sum of several steps. Okay, so we can do calculations like this. If given the values of several intermediate states, we can find delta H total, or we can solve for one of the intermediate values. But there are a couple of rules that we need to use when we are adding and subtracting these values. So let's be clear about what those are. So rule number 1. There's going to be a particular delta H value for each reaction. And when we multiply those reaction coefficients by something, we also need to multiply the delta H value by the same number. So let's look at this first one, and we see that this is a nitrogen gas plus oxygen gas goes to 2 molecules of nitrogen monoxide, and that reaction has a particular standard enthalpy value. Well, maybe I just want to talk about 1 molecule of NO. So I want to change the reaction by multiplying it by 1/2 to make 1 of NO at the other side. And so what this rule says is if we multiply the reaction coefficients by 1/2, I also need to multiply my enthalpy by 1/2, because this enthalpy is specific to this particular reaction that makes 2 moles of NO. So now we can write this again as 1/2 nitrogen gas plus 1/2 oxygen gas makes just 1 mole of NO gas. And the new delta H standard value for this reaction is half of the original, 90.25 kilojoules. Okay, the second rule is really just an extension of the first one. And this is about if we want to flip the reaction the other way. So if we want to reverse a reaction direction, we need to reverse the sign of our delta H value. Okay, so this reaction that we're using as an example, nitrogen dioxide breaks down into nitrogen monoxide and half an oxygen molecule with a particular delta H standard value. And let's say that I really want to talk about the formation reaction going to the right instead of this decomposition going to the left. So if I were to flip the reaction, that's kind of like multiplying the reaction by -1. And according to the first rule, when we multiply a reaction by something, we multiply the delta H by the same. So we would multiply delta H by -1 as well. I like to think of it that way because then I don't really have to remember as many rules. So now we can flip the reaction with the reactants and the products on the other side, and we flip the sign of our delta H value as well. Piece of cake, no problem. So our third rule here is the real meat and potatoes of Hess's law, and that's about adding reactions together. Because that's what we're trying to do in these pictures, is we're trying to say if I add several different reactions together, I can get a new total reaction, and that relationship is useful. So when we're adding the reactions together, we need to add the delta H values together for each of the steps. But before we add them together, we need to make sure that those reactants add up to the correct total. Usually you'll have a particular large reaction in mind, and you'll be looking for the individual steps. And you might need to do things like multiply by coefficients or flip the reactions in order for all of the parts to add up to the total. So let's take those pieces that we were just talking about in the previous one. So our 1/2 nitrogen gas plus oxygen gas forms nitrogen monoxide with the particular standard enthalpy value. And if we use the second reaction takes that nitrogen monoxide, hold on, I missed a 1/2. There we go. So the second reaction takes that nitrogen monoxide and mixes it with a little bit more oxygen to form nitrogen dioxide gas. And that one has a delta H standard of 57.07. And you can see that these reactions can happen consecutively. And so if I want to find the total reaction, I can just add these reactions together. And remember that if something is on the reactant side and the same thing is on a product side, it will cancel. So we have 1 NO on the reactant side and 1 on the product side, so those are going to cancel out. We also have 2 O2 terms, but they're on the same side, so they will add. So we've got a 1/2 nitrogen. We have 1/2 plus 1/2 equals 1 oxygen gas. The nitrogen monoxides are gone, they cancel out. And there's 1 mole of nitrogen dioxide left. So now I have a total reaction that would happen if these 2 steps happened consecutively. And if I want to find the delta H value for that total, I add the previous pieces together. So 90 minus 57 is positive 33 kilojoules. So this is the type of process you will need to go through to find the total enthalpy value for a process based on several individual steps. You'll need to rearrange the particular steps so that they cancel as they should by reversing them or by changing the coefficients and remembering to do the same for the delta H value.